So we're on your chemistry, chapter 3, section 3, and we're going to be talking about the mole. Probably you've never heard about this before, but it's not going to be as complicated as you think. See, basically the most basic relationships in matter are those based on the numbers of atoms, ions, or molecules, not those based on masses. In this section, you will learn how to convert the number of atoms and molecules to mass. How to weigh it. How do we weigh atoms and molecules? Well, we're going to find out how to do that, right? To weigh it, it sounds complicated, but it's not as complicated as you think. So, the molecular mass is the sum of the atomic masses of all the atoms in a formula of a compound. Whether the compound is ionic or molecular, the procedure is the same. Examples, okay? So, we want to find out what the molecular mass of each of the following compounds is. Sodium chloride. This is just the molecular mass. How much does this weigh? So you can look on the periodic table and you're going to be able to find the mass. But how do you find it when it's a whole molecule, not just an element? So the formula for sodium chloride is NaCl. Thus the molecular mass is calculated by adding the atomic masses of one sodium atom and one chlorine atom. And you see there? So you have the measurement of sodium chloride, that mass, is going to equal the mass of one sodium and one chloride. So we look up those atomic masses on your periodic table. You can look and find out. We did that so that we know that the atomic mass of sodium is 22.99 units. You go by units. And then you know that the mass of chlorine is 35.45 units. So if you add these together, you're going to get the mass of that molecule is 58.44 units. It's just adding up all the molecular masses. So let's do a little more complicated one here. So we have dinitrate pentoxide. It has a molecular compound with the formula N2O5. Okay, so we look and we find out basically what is the molecular mass of nitrite, and we have it 14.01 units, and we need two of those. So we times that by 2. And then we take the 5, we need 5 of oxygen, and oxygen is only 16.00 there. And so if we multiply and calculate 2 times 14.01 times 5 times 16, and we're going to put those together, and we're going to get 108.02 units, because we have to make sure we sig figs of 0.02, because that's what's in our addition is point. We can't go any less than that, right? So it's going to be 1.08.02 is going to be our answer. Just adding up those from their masses that you get right off the periodic table. And we learned how to do that. So now we're going to have carbon dioxide, and we're going to add that up. So we look here, and so the mass of carbon we know is going to be 12.01 unit, and the mass of oxygen we know is 16.00. And there's going to be 2 oxygens, so we're going to multiply that by 2. So 2 times 16, and then we're going to add 12, and we get 44.01 units. That's how you find the mass number. So now we want to find what is Avogadro's number. Avogadro's number, what is this? Well, let's find out. To relate microscopic values like atomic masses to the microscopic values measured in the laboratory, chemists have to use Avogadro's number, because we can't really weigh those tiny atoms, can we? So we're going to have to take a bunch of atoms and weigh them. And how do we get this number? And this is how they got avocados. I would say avocado, but Avogadro's. Just remember, like avocado. That's how you remember it. It's kind of like avocado, but it's Avogadro. It's a guy's name. So right here, Avogadro's number. So is the number of atoms in exactly 12 grams of carbon, 12. And so what they did is since the atomic unit is defined so that an atom of carbon has 12, and a 12 unit, a mass in grams numerically equal the atom or molecular mass in atomic mass units will contain Avogadro's number of atoms or molecules. So if you look right here, you have 12 grams of carbon and it will contain 6.22 times 10 to the 23rd. This is a huge number because we're talking about atoms and making atoms big enough to weigh or whatever. So here we have. So that's of carbon 12. So then with the carbon 12, it's going to take, 16 grams of oxygen, and you're going to times that, or basically you're going to multiply that by Avogadro's number, which is 6.022 times 10 to the 23rd atoms of oxygen. And so if you're going to take CO2 as carbon dioxide, so you're going to find out and add up the carbon and add up the oxygen, you get 44.01. Then you're going to multiply that. That's going to be contain 6.022 times 10 to the 23 molecules of carbon dioxide. So as you see here, so Avogadro's number is the link between the microscopic and the macroscopic, the very tiny, tiny atoms to those big enough that you can weigh them. So just remember, what is Avogadro's number? It's 6.022 times 10 to the 23rd. That's a huge number, like I said before. Avogadro's number is an extremely large number. It is difficult to appreciate the magnitude of such a large number without some analogy. So, electric counter capable of counting 10 million objects every second would require almost 2 billion years to count it. So if you were counting 10 million things a second, it'd take you 2 billion years. That's how big Avogadro's number is. Avogadro's number of P's is approximately of each P is like 1/10 of a cubic centimeter, or a centimeter, I should say, in volume, would cover the entire United States at the depth of 8.88 kilometers, which is 5.51 miles. Avogadro's number is huge. However, atoms and molecules are so small that Avogadro's number of iron atoms has a volume of only 7.1 cm squared. So that is amazing. So now we're going to talk about a mole. Well, we talked about Avogadro's number. Now, what is a mole? Well, a mole is a term that is nearly synonymous with Avogadro's number and is a mole. So a mole is abbreviated MOL, is Avogadro's number of anything. So basically a mole is Avogadro's number. So we don't have to say Avogadro's number all the time. We know what that number is, but now we're just going to call it a mole. From another standpoint, a mole is the amount of substance containing the same number of particles as exactly 12 grams of carbon at 12, just as this pair of two objects, a dozen, 12 objects is a score of 20 objects, a gross is 144 objects. So a mole is Avogadro's number times that, which is 6.022 times 10 to the 23rd. That's how much you have to multiply. That's a huge number. We can have a dozen eggs, a dozen donuts, a dozen people, or a dozen bees. Similarly, we can talk about a mole of ions, a mole of atoms, a mole of marbles, a mole of peas, and so on. Just by multiplying that huge number, we can say we want a mole of it, as long as we specify the object. Because Avogadro's number is very large, however, using the mole is practical only when referring to the microscopic world because it's so large. So here we have this picture here. So we're going to have a mole of carbon, a mole of glucose, a mole of water, gold, sulfur, copper, a mole of helium. And that's what we have. It's the measuring. It's how we can measure it at a mole. And a mole is whatever the tiny atom times Avogadro's number, which again is 6.022 times 10 to the 23rd. This is just a way of measuring, instead of measuring tiny, tiny atoms, which we can't weigh, we can measure a mass of them. So let's see. It says, now we have a practical means of relating uncountable numbers of atoms, molecules, to measurable quantities of mass. So it would be impossible to count out all of these, 6.22 times 10 to the 23rd. We couldn't. It'd take a billion years or whatever. However, you simply weigh out one mole, that is 44.01 grams, you will have, and times that, you will have 6.022 times 10 to the 23rd molecules. So this is how we weigh it. So weighing objects to obtain specific numbers of them is not restricted to chemistry. It is used in everyday life. For example, in a factory, if you have large numbers of tiny parts, such as little springs, are you going to count all those little springs out? No, you're going to weigh them to find out. Similarly, grass seeds are not counted out, but they're sold by the pound. The relationship between the numbers of particles and moles are summarized below. You got to look at, they show you how they figure this out. Let's see. Right here, there's Avogadro's number and how it comes into mass number. So you can look at that. It will help to realize that 1 mole of a substance contains Avogadro's number and has a certain mass. Thus, a mole is the link between mass number and particles that we can weigh out and find out exactly how much we have of that element. When we can't get down to the tiny, tiny atoms and weigh them, we can use this big number to weigh them. It's pretty handy. So now I'm going to go over these examples here. So what is the mass of 0.40 moles of copper atoms, which means mole is an Avogadro's number. So you're given the value is 0.4, and so the new information is the mass in grams. So we need to know, assume that the mass should be expressed in grams unless otherwise indicated. So you're going to say it's in grams. So number 3 says we know that the molar mass gives the relationship between mass and moles of a substance. From the periodic table, we find out what the atomic mass is. So what's the atomic mass of copper? Look on your table and you'll see the atomic mass is 63.55 units. And thus, the molar mass is going to be 63.55 grams. Wow! So all we have to do is find out what the units are, what the atomic mass is, and then we can know what a mole is going to be basically that same number. And a mole, to convert the number of moles to mass, multiply the molar mass number. So now that we know how many, now that we know what the mass is, so we know the mass, so we're going to solve it. So now we go down, number 4 here says molar mass, NM. So we're going to have basically, we know that 63.55 grams will be our mole, and we're going to times that by what? That 0.04, because that's what the equation says. It says, what is the mass of 0.04? So we found the copper atoms, what the molecular mass is with a mole. And so now we know it's just basically we take 0.40 times 63.55 grams, and we'll get 25 grams. Is the answer reasonable? Yes. 1 mole of copper would have a mass of 63.55, and 25 grams is less than half of that because we're going by 0.4, and so they are fine. So that's how you do. Basically, you're just going to take that copper and find the atomic mass and turn it to the Avogadro's number and then times it by 0.4, like almost half of that. Okay? So what is the molar mass of sucrose? Okay, this is a little bit big because now we're going to have to find out each one of those. The given information is the formula for sucrose. So we have that. The new information is the molar mass. So by definition, the molar mass is the mass per mole of substance, which we know. From the formula, we know that 1 mole of C2H12O11 contains 12 carbons, 22 moles of hydrogen, and 11 moles of oxygen. So now we got to times that all out, don't? Molar masses of atoms can be found in the periodic table. So we look in the periodic table. First one, so we have, first of all, 12 of those, 12 carbons. So we know carbon is 2.01. And so we're going to multiply 12 times 2.01, we get 144.1. And then we have 22 hydrogen, so 22 hydrogens, so we know that the mass is 1.008. We find that in the periodic table and just times it by 22. And then the oxygen, we know is 16. 11, so we have 11 oxygens times 16. And so we multiply that out and we get 176.0. So now we add that all up and we'll get, we add up the 144.1, 22.18, 176, and we get 342.28. So, which we're going to have to go to the sig fig of the lessest sig fig, which is going to be 0.0, because we have oxygen being 0.0. So, we're going to have to go to the decimal point. So we can round that to 432. Let's get that out of the way. 432.3 for sig figs. So the molar mass of C12H22 and 011 is going to be 342.3 grams per mole. So, a relatively large molar mass is expected since sucrose contains a reasonably large number of atoms. And so we have a large amount. The numbers in the formula are exact whole numbers, so you can check each one. So anyway, so we're going to learn how to do those. So the concept review here. So let's see about that concept review. What units are usually used to express molecular mass? So Avogadro's number, right, is a mole. So mole is Avogadro's number. It's basically times that. How many molecules of hydrogen are in 1 mole? So if we have hydrogen, we look on the periodic table, and hydrogen is 0.008, and so we're going to how many moles? We're going to times that by 2, right? So you get the number times 2. So 1.008 times 2, because there's 2 hydrogen molecules. To find molar mass, okay? Molar mass is what? Avogadro's number of particles has certain mass. So mole is the link between the mass number of the particle and the molar mass of a substance. So basically it's making these tiny particles and taking Avogadro's number to make them a mass, to be able to measure them, right? Okay. Calculate the molar mass of each of the following. So let's see if we can do that. Okay, here's how I did it here. So we have methane, CH4. Well, we looked it up in the periodic table. C is 12.01 and hydrogen is 1.008. And so since we have 4 hydrogen and 1, we have 12.10, 12.10, and we're going to times that, what did I say, CH4. So that's just going to be 1. Anyway, we're going to times that by, what did I say here? Oh, right here, 12.101 plus 4. See right here, 4.1008. So 12.100 times 4.032, because we times that by 4. So it's going to be 16.042 on your calculator if you just added those. But then it's only going to be you only can go to the sig figs of 4. You have to round it off. So it's 16.04 grams. Okay. So now the next one we have xenon hexafluoride. So which is xenon with hex means 6. So XeF6. So Xe, if you look that number on your periodic table, you get 131.3. And then fluoride is going to be 19. So it's going to be 141.3 plus 114, because you take 6 times 19 and you get 245. So let's do the next one here. These are C27H46 is a huge number, and 1 oxygen, right? Is that what it says there? Yeah. No, it says oxygen 11. Okay, so I missed that out, so it's oxygen 11. Anyway, what you're going to do with this problem here is basically find out what the carbon is, and the carbon's going to be 12.01, and times that carbon by 27, and the hydrogen is going to be 1.008, and you're going to times that by 46, and then the oxygen is 16, and you're going to times that. Oh, it's just 16, so I was right. Say 27. I thought it said 11. Okay, where is the number? Right here. So in adding all this up, you're going to get 386.638, and you're going to go to the second sig fig, of course, so it's going to be round to 386.64. So you just, all you do is add those up. 12 is the 0.01 times 27. Hydrogen is 1.008 times 46 and 16. And so that's the number you get. Okay, number 2, assume that you are given, here, let's read it up here. Assume that you are given 0.44 moles of a substance. How many atoms are present if the substance is lead metal? Okay, so basically we're going to look if you're giving that. So what you do here, you have 0.44 of the substance. Well, here's lead. So you look up what lead is. 207.2 times 0.44 is all you do. And you end up, as you multiply that out with all of your decimal, you're going to get 91.168, which is going to, using your calculator, is going to be 92 grams. So B, how many atoms are present, or how many molecules are present if the substance is sucrose? That's the C12H22O11, which I thought before. So I have C example. Anyway, you're going to have to take each one of these and times them out. In the example we had before, see the example we had before. Let's see. I don't know when I had the example before, but I have C example. Must be the example I had in your. Let's see. Right here. Here's the example. So we have 342.3. It's already done for us. They added them all up, right? So that's why it says C example. Okay. So we have the C example, and now we're going to times that, which is 0.44 times 342.3. And so as we do that, we're going to get 150 grams. So the next one is calcium carbonate. So we have 40.08 times 12 times 3. Anyway, as you find that, you'll be able to find that. I have my calculations all here. So anyway, you can do that easily by just finding and then timesing it by 0.44. Anyway, let's go on to, it says, give the molecular mass of each of the following substances. So this is a little easy. So we have zinc, and we looked it up, and it's 65.38 grams. We got AgCl, which is silver chloride, and Ag is 107.9 and plus 35.45, and you get 143 there, and you round it to 143.4. Just look these up in your periodic table. O2 would be 2 oxygen. Well, oxygen we know is 16. 2 times 16 equals 32. 32 grams. And then sodium 2 sulfate there. And so we have sodium is 22.9. Sulfur is 32.06. And we have, we end up having sodium is 45.98 plus 32.06 plus 64, because as you times this, oxygen there is going to be 16, so 16 and it's 4. So anyway, see how I did that? Anyway, so I will help you do these as you want it, but they're not that hard to do. Basically, you have to find the molecular mass of them, and then change it to, through the Avogadro's numbers, could be grams. So you're just taking the very small and making it very big.